Path integral capital I sub Roman numeral 3 takes us from little r plus I in the first quadrant over to little r minus I on the left in the second quadrant. Along this path, z is equal to x plus I and dz equals dx, with x being equal to z minus I. So if we substitute in values for x in place of z, and do be careful with the bounds of integration, then we can get something that looks similar, though hardly identical, to capital I sub Roman numeral 1. Our next move is to separate the exponents in the numerator of the integrand. Similarly, the right-hand term in the denominator can be broken into negative 2 pi x and negative 2 pi I components. E to the negative I may be pulled outside of the integral, and we are free to extract a minus sign along with it, provided that we reverse the bounds of integration. In the denominator, we take note that e to the power of negative 2 pi I is equal to positive 1, and for our purposes, disappears. As with the previous two path integrals, we conclude by taking the limit as little r approaches infinity. In the case of capital I sub Roman numeral 3, the limit as little r approaches infinity gives us negative e to the power of negative I times an integral that happens to be the one that we're looking for. Evaluation of the path integral capital I sub Roman numeral 4 basically amounts to a rehash of the methodology used for Roman numeral 2. We follow a path along the left side of the contour starting at negative little r plus I, going down to negative r plus 0. Along this path, z is equal to minus little r plus iy. Differentiation of z gives us a value of dz equal to I dy. Next, we substitute the values for z in terms of y and dz in terms of dy. In the case of the bounds of integration, we may omit little r and the factor of I since we are integrating with respect to y alone. Next, we break up the exponential in the numerator into factors of e to the little r, positive little r, since we are multiplying two minus signs, and e to the negative iy. In the denominator, we factor the second term into e to the 2 pi little r and e to the negative 2 pi iy. Next up, we take the absolute value of the integrand. Just like we did with capital I sub Roman numeral 2, we will separate the numerator from the denominator. From here, we can break the numerator into separate factors. The absolute value of I is 1, as is the absolute value of e to the minus iy, and this leaves us with the absolute value of e to the power of little r on top. Isolating the absolute value in the denominator, we factor out a minus sign from the second term. Utilizing the reverse triangle inequality, we can say that the aforementioned denominator is less than or equal to the absolute value of the difference of the absolute values of the original constituent terms. Focusing on the right-hand side of the inequality, we can separate the two exponentials on the right into separate absolute values. The variable y is real, and the absolute value of negative e to the power of minus 2 pi yi is equal to 1 for all y, so we can cross it out. Both of the remaining absolute values of 1 and e to the power of 2 pi little r are positive for real values of little r, so we are free to remove the inner absolute values. This leaves us with the absolute value of 1 minus e to the power of 2 pi little r. So if we take three of the previously described formulas and combine them, we can say that the absolute value of 1 plus the product of e to the power of 2 pi little r and e to the power of negative 2 pi yi is greater than or equal to the absolute value of 1 minus e to the power of 2 pi little r. Taking the reciprocal of both sides reverses the polarity of the inequality. From here, we multiply both sides by the individual absolute values of e to the power of little r, e to the power of minus iy, and one lonely-looking factor of I. We combine the terms in the numerator on the left-hand side. On the right, we take notice of the fact that two of the terms in the numerator are equal to 1 for all real values of y. This leaves us with a solo absolute value of e to the power of little r. So using methods previously discussed, we are welcome to combine the numerator and denominator on the left-hand side into a single absolute value. We then integrate both sides of the inequality with respect to y, utilizing the same boundaries as that of the path integral capital I sub Roman numeral 4. The integral on the right-hand side of the inequality has no y dependence, so we are free to separate the absolute values from the integral itself. Solving the integral on the right is trivial, and we are left with minus the absolute value of e to the power of little r divided by the absolute value of 1 minus e to the power of 2 pi little r. Focusing back on the left side of the inequality, the integral inequality allows us to say that it falls on the right side of the inequality involving an absolute value where the signs encompass the entire integral instead of just the integrand. Capital I sub Roman numeral 4 can be substituted inside of the absolute value signs on the left side of the inequality. Combining this inequality with a previous inequality involving little r gives us a triple inequality involving both little r and capital I sub Roman numeral 4. Dropping the midsection of this inequality gives us a formula for the absolute value of capital I sub Roman numeral 4 in terms of little r alone. Next, we take the limit of both sides as little r approaches infinity. On the right-hand side of the inequality, we divide both top and bottom by e to the power of little r. Since e to the power of little r is positive for all values of little r, it can be absorbed into both sets of absolute value signs, giving us a 1 in the numerator. The first term in the denominator goes to 0, whereas the second term goes to infinity because its exponent is a positive number. Detonation of the denominator gives us 0 on the right side of the inequality, and we can say that the limit of the absolute value of capital I sub Roman numeral 4 is less than or equal to 0. Since absolute values cannot be negative, we can say that the limit as little r approaches infinity of the absolute value of capital I sub Roman numeral 4 equals 0. Finally, the fact that the limit of the absolute value of capital I sub Roman numeral 4 is 0 means that capital I sub Roman numeral 4 itself is 0. Fun fact, the minus sign implies a 0 value for capital I sub Roman numeral 4, since the rest of the expression on the right is positive. Let's now take another look at the contour integral capital I sub L, and of course the limit of it as little r approaches infinity. The limit is, of course, equal to the limits of the 4 path integrals that we just evaluated. Limits corresponding to Roman numerals 2 and 4 are equal to 0, and we are left with two factors of the improper integral that we came here to solve in the first place. Both the contour integral and its limit as little r approaches infinity have been shown to equal 2 pi I times the residue of f of z at positive I over 2. This gives us an equation that allows us to solve for the improper integral in question. The left-hand side simplifies to 1 minus e to the power of negative I times the improper integral. On the right, we substitute in the value of the residue, and a factor of 2 pi conveniently disappears. Next, we multiply both sides by e to the power of positive I over 2, and this causes the exponential terms on the right-hand side to disappear. On the left, we simply distribute the exponential across two terms. On the left-hand side, Euler's relation allows us to expand two exponentials in terms of trigonometric functions. Cosine is an even function, and this allows us to ignore the minus sign within its arguments in the expression for the second exponential. The first and second cosine functions cancel, and we next focus on the fact that sine is an odd function. A minus sign located within it can be moved outside of as a multiple of the sine function. This allows us to combine the first and second sine functions. This leaves us with 2i sine 1/2 times the integral on the left side of the equation, and the i's cancel. Dividing both sides by 2 sine 1/2 means that it's time for a cup of coffee. Till next time, this is Pentagram Prime signing off.